Let me first start my presentation by thanking the organizers, Professor Young and Professor Wang, I think. I appreciate the efforts to put this symposium together, and I'd also like to thank Professor Han for giving this introduction. I've been in and out of the session because I had to go to a different session too, but when I was in the session, I saw different presentations talking about completely different topics. So I figured that I would go about my presentation in the basis that at least some people in this room may not know what the materials that I'm dealing with are, which is nanocrystal quantum dots. Some of you, so those who are familiar about quantum dots, can just bear with me for one or two slides, but for those who are not truly familiar with this material, this is semiconductor nanocrystals that show the quantum confinement effect when the size of the materials is smaller than the typical separation between electron and hole in bulk space. Then when the size becomes really small, what happens is that the electron and hole wave function fills this boundary, and because of this confinement, electron gap is going to change. And it's going to change as a function of the size, and you can tune this energy gap using the size of a material, and with one composition, one set of composition on one set of material, you can make materials that emit light in different color, different wavelengths. So you can realize RGB theoretically within one material. Now there's a problem about blue emission at this point, but I'm not going to too much detail about blue emission for today's discussion. But my point is RGB colors can be realized using one set of materials. But you have to choose right material. Outside of that, the beauty of this size tunability is that you can create different colors. Because of the efforts by Korean companies, let me move to this side. Because of the efforts by different display companies and set companies, quantum dot materials are projected to be demanded by market over the next few years, which means that people who are working on quantum dots may have a better chance of getting funding from different sources. I hope this will be true in the future, but for this to be true, you have to have a good materials and good material for commercialization in many aspects. You have to think about stability, you have to think about the material toxicity, you have to think about all other things. So if you think about this, of course, quantum dots can be made in several different ways. You can classify the synthesis into two, one being physical method. You can bombard your substrate with very high energy and create crystals within a matrix, which typically people call epitaxial quantum dots. Using high vacuum chamber equipment, for example, molecular beam epitaxy creates these finely size-tuned quantum dots within a matrix. Or you can make nanocrystals or these quantum dots in chemical way. Chemically synthesized quantum dots. Colloidal quantum dots is one very important example. Simply, you inject your chemicals or precursors into hot solution, or sometimes it can be less hot, it can be really, really hot, but you bring the molecules into this reaction and then let it go for sometimes for seconds, sometimes for several minutes to even hours, then you come up with quantum dots. You can clearly see that if you have this relatively expensive equipment, the chances are that you can make quantum dots in very uniform size. So size uniformity can be better in many cases, and because it's embedded in the matrix, there's less of a problem on surface oxidation. But in the case of colloidal quantum dots, the problem is obviously when you have crystals growing through this homogeneous nucleation, size uniformity will be a problem. Now let me go back to the previous slide. I didn't mention about the contrast between quantum dot based displays and other displays. Quantum dots are attracting attention for many reasons, but the primary selling point is that the quantum dots can have very narrow emission. And it's going to result in very high color purity and color representation. So that means you have to have very uniform size within the material. And this particular image, if you compare these two, it looks as if these epitaxial quantum dots are more uniform in size, and rightfully so, because you use very expensive and exquisite control of this synthesis condition. But colloidal nanocrystals are a little more, a little less uniform in size. With the progress in the past couple of decades, this size uniformity has been addressed almost to the perfection. So the bottom line of this synthesis of colloidal growth of nanocrystals is that first you need to have emitting layer, the core that's going to emit light, and you have inorganic shell that's going to protect the core from oxidation and other types of reactions. And I'm not going to talk about these effects on thick shell and interfacial defects for today's discussion, but shell is also playing a very important role. How thick the shell is going to affect the other optical properties. Ligands are very important as well. Typically, organic surfactants are used for these chemical ligands that's going to protect the surface from oxidation, but also size uniformity is also warranted by having proper set of ligands. Today I'm going to spend my lot of time on the cores, how we make cores, and how one of the approaches that we get in the context of size uniformity, and how in the second section I'm going to talk about how shape control was achieved in our case. So because I know and I think there are diverse people from diverse backgrounds, I have a lot of slides, but I might skip some of the more nitty-gritty slides. So if you have any questions during the talk, please feel free to stop me at any point. Indium phosphide quantum dots are one of the materials that can meet some of our requirements in terms of realizing RGB colors. So there's a controversy, or there's still unanswered question about blue, but RG, for example, can be, red and green can be synthesized using indium phosphide quantum dots. People are trying to make blue indium phosphide quantum dots as well. So indium phosphide, compared to what people have studied for many, many years in cadmium selenide, indium phosphide has no cadmium, so cadmium free, so relatively less toxic, and because of the energy gap of indium phosphide, it's being studied a lot. Now the problem is, compared to ionic crystal, more ionic bonding in cadmium selenide, indium phosphide bonding is a little more covalent. It's typically when it becomes a little more covalent or less ionic, it makes it very difficult for us to make an controllable synthesis. So the result of indium phosphide growth, if you just follow the recipe on cadmium selenide nanocrystals and use indium phosphide instead, what happens is the size uniformity is getting a little poor at the first. If you just simply following the recipe. Now, polydispersity in indium phosphide quantum dots results from a couple of reasons. First, this mainly what is called TMSP, the phosphine precursor, is very, very reactive. And this reactive phosphine precursor is going to result in relatively poor size distribution. So the question in this particular case is going to be, how do we slow down the reaction? And previously, in one article, we ran into this article that says zinc. If you dope this material with the zinc, somehow emission is narrow, and we wanted to look at it in terms of reaction mechanism in the indium phosphide growth. So in the following slides, I'm going to talk about how the introduction of zinc has to do with the uniform size of indium phosphide quantum dots. So we prepared different samples, indium phosphide nanocrystal growth control, and then we also put zinc and phosphorus. And this zinc precursor, usually zinc precursors are less reactive than many other precursors. So zinc is very slow reaction, and we put zinc precursor in here, so we have zinc and indium and phosphorus all together. So there are a lot of curves and plots here, but for the interest of time, I'm going to go on the quick highlight. When you put zinc compared to indium phosphide, no zinc, you can see that there's a peak showing up in the case of zinc. So even in some mild conditions, you start seeing the evolution of this peak. What does the peak mean? The peak means that there's now relatively narrower size of indium phosphide formed as a result of zinc introduction. And you can see that the y-axis is wavelength of the absorption. Typically, when the size is larger, then wavelength is in the longer range. So you can see from these two samples, by putting zinc, you basically slow down the reaction. It's getting slower compared to the red dot, which is indium phosphide. So by putting zinc, we can also see that it's getting slowed down, and the question of course is why we have slow growth of indium phosphide. And we ran a lot of different characterizations, so following slides may be a little redundant, and it's going to be over and over again, but NMR spectra, basically NMR spectra, and then mass spectroscopy data that's going to follow this slide shows that when zinc is introduced, let me go to this slide. So Alditov mass spectra, when zinc is introduced, now there's a new set of chemicals that are formed that's indicating the formation of zinc and phosphorus bonding. And instead of indium and phosphorus bonding as an intermediate species, now you get zinc and phosphorus bonding, so that's going to replace phosphorus precursor intermediate species. And the reactivity of this is a lot slower than the reactivity of indium phosphide intermediate species, and it's going to slow down the reaction. So we also ran computations on the reactivity or stability of the zinc phosphorus species or indium phosphorus species, and from these we were able to identify why zinc introduction has to do with this slow reaction. So we put zinc, and depending on when zinc is introduced, so we put zinc first and then indium, first zinc first and then inject indium later, and then indium phosphide first and zinc later. And you can see that by looking at the peak positions, when zinc is first introduced and form this zinc phosphorus precursor first, and then indium is later introduced, that because of the slow decomposition of zinc phosphorus precursor, now you get a relatively smaller growth of the crystals, and it's going to also affect the peak narrowing of the PL spectrum. So the bottom line is when you introduce zinc, because it's going to change the way the precursor intermediate species is formed, it's going to now change reaction kinetics, and therefore you get narrow emission like this. And so this is the quick overview of indium phosphide quantum dots when its synthesis is controlled by simple introduction of one precursor, one chemical in zinc. And we also explore, in our lab, we also exploring low-dimensional nanocrystals, such as nanorods and nanoplates. And our primary interest is on polarized emission that comes from these anisotropic growth. Compared to spherical or semi-spherical quantum dots, when you have nanorods or nanoplates, when they emit, because of the dielectric moment aligning to the long axis of this anisotropic species, you tend to have polarized emission, whether it's linearly polarized emission or circularly polarized emission, you get some polarized emission. And we have some data on primarily on the polarized emission, but today I'm going to discuss the growth of these one-dimensional nanocrystals. So for this, we had to use cadmium selenide, not indium phosphide, because of the crystal structures. Which I mean that if you need you need some hexagonal structure or anisotropic crystal structures of material to grow one-dimensional like this. Now, to grow one-dimensional crystals like this, you need to have some motivation or some driving force that create anisotropy in growth directions. By modulating the ligand on the surface, we were able to make dual diameter nanorods for the first time. And the beauty of this structure is that we can actually study the growth of this direction versus this in very long time. It's very difficult to see when you have a single diameter nanorods, because it's going to look the same regardless. But if you have these dual diameter nanorods, now you start seeing the growth direction in this way and that way, and you can monitor the growth patterns over time. We used two different ligands, shorter ligands and longer ligands, both are phosphonic acids, and put them and then grow in colloidal batch. And then by monitoring the growth of nanorods, you can see that growth is going to be drastically different. You can see that there's a thick nanorods forming, and then later you have extrusion of this smaller nanorod components, and then you see the growth of smaller nanorods more drastically in longer time. Basically, because of the passivation of the surface layers using hexyl phosphonic acid and octadecyl phosphonic acid, and their interplay on the surface, we were able to get this thin diameter nanorod tail. And as you can see, the beauty of this approach is to be able to measure the length over time and record it, and then get this time scale or growth rate scale, and without having to take samples over seconds or milliseconds. You can do this by taking samples out of the reaction for every minute or every 2 minutes, and then you will be able to see how fast it grows in one direction versus the other. And from the studies, and I'm going to probably skip some details of the studies, but we were able to identify that the monomer, the ligands on the surface, is playing a very important role in whether the monomer is diffusing through this monolayer better or not. By changing the monomer composition or the ligand composition, we were able to see the control of the growth. And by using hexylphosphonic acid or octadecylphosphonic acid and their interplay, like between the two ligands, we were able to get a different fraction of octadecylphosphonic acid will result in different growth rate, especially in thick nanorod parts. Once you do that, skip this. Once you do that, now you can change the growth reaction in 0001 direction versus 000-1 direction of the nanorods, and this was not. You cannot really observe this without having dual diameter nanorod structures like this. And by doing so, we were able to change the core position. So there was core within this nanorod. You can change the core position by simply controlling the growth rate. For example, in this case, core is at the tip of the nanorod, and in different cases, you can move this core into the center, the middle of the nanorod. This optical properties data will show you how electron-hole separation is controlled by changing the nanorod dimensions. Some of the polarization study data show that the nanorod dimensions, especially the short component data here, short aspect ratio part, is going to affect the nanorod polarization properties a lot more than other cases. So with that, I'd like to conclude that there are so many other activities going on within our group. We are interested in controlling the growth of the nanocrystals for making nanocrystals commercially viable and sort of more controlled for display applications. We are also interested in the growth of nanorods and their use in polarized emission medium. And this is my group, I think of last year. I highlight two hardworking students, two students that are not playing around, they are working really hard. Of course, the rest of them are working hard too, but Songjun contributed a lot in the indium phosphide nanocrystals that I presented today, and Dahim was working on the nanorod project. And I also like to give a special thanks to Dr. Wan Ki-bae at KAIST. Thank you for your attention.